More than 4,000 years ago, on a sun-baked plateau outside modern Cairo, a civilization with no iron tools, no wheels for hauling stone, and no written mathematics as we know it today, raised a mountain of limestone and granite, so precise that its base is level to within a few centimeters across more than 5 hectares of desert. Somewhere in the mountains of Peru, another people would later carve an entire city into the spine of the Andes, fitting stones together so tightly that a knife blade cannot slide between them. Without mortar, without iron chisels, in a place where a single earthquake could topple lesser structures in seconds. And in the Bekaa Valley of Lebanon, ancient hands would quarry, move, and lift blocks of stone weighing more than a fully loaded jumbo jet, stacking them high enough to support a temple platform that has outlasted empires. How did they do it? That is the question this film is going to sit with, turn over, and try to answer, not with legend, not with fantasy, but with the evidence stone itself has left behind. Picture the scene. Dawn breaks over the Giza plateau. Long shadows stretch across the sand as thousands of workers begin to move, ropes coiled over their shoulders, the low murmur of coordinated labor rising with the heat. Cut to the misty peaks of Machu Picchu, terraces disappearing into cloud, granite walls glowing faintly gold in the first light. Cut again to Baalbek, where 3 stones larger than almost anything ever moved by human hands, before the industrial age, sit stacked in a wall, patient and unexplained for 2,000 years. These are not separate stories. They are chapters in the same story, the story of how human beings, armed with nothing but wood, rope, fire, water, copper, bronze, and an almost unbearable amount of patience, built things that by every modern measure should not have been possible for people without machines. This is Ancient Engineering Files, and today we are asking how civilizations across the ancient world built the impossible. To understand why these achievements still baffle engineers today, we first need to understand the worlds these builders lived in, because the impossible was never built in a vacuum. Egypt's pyramids rose during the Old Kingdom, a period of extraordinary centralized power, when a god-king could command the labor, food supply, and logistics of an entire nation for decades at a time. The Nile itself was the circulatory system of that civilization, flooding every year to deposit fertile soil and, crucially, providing a highway of water on which stone could be floated from quarries hundreds of kilometers away. Picture a papyrus map unrolling across the screen, tracing the river's path from the granite quarries of Aswan in the south to the limestone cliffs of Tura near the capital, arrows showing barges loaded with stone drifting north on the current. Without that river, the pyramids as we know them simply do not exist. Half a world away and roughly 3,500 years later, the Inca were building an empire along the spine of South America, a civilization that never developed the wheel for transport, never used iron, and had no system of writing in the way we understand it, yet somehow administered a realm stretching over 4,000 kilometers of some of the most vertical terrain on Earth. Their capital region around Cusco and their retreat at Machu Picchu sat in a landscape defined by earthquakes, steep cliffs, and thin mountain air. Every structure they built had to answer to gravity, seismic shock, and altitude all at once. And in the Bekaa Valley, Baalbek's massive foundation stones were laid down under the influence of a rotating cast of civilizations, Phoenician, Greek, and later Roman, each one adding to a religious complex that ancient peoples clearly regarded as sacred ground worth extraordinary effort. 3 different climates, 3 different political systems, 3 different toolkits, and yet 3 sets of builders who each decided that the ordinary limits of construction simply did not apply to them. Now let's get into the engineering itself, because this is where the story stops being mysterious and starts being genuinely staggering. At Giza, the core challenge was scale multiplied by precision. The Great Pyramid contains an estimated 2.3 million blocks, some weighing as little as 2 tons, some granite blocks inside the king's chamber weighing closer to 80 tons, all fitted together to form a structure that was originally sheathed in polished white limestone casing stones, cut so precisely that ancient visitors described the pyramid as blinding in direct sunlight. Show a CGI reconstruction here. The pyramid gleaming white with its golden capstone catching the sun, a visual almost nobody alive today has ever seen with their own eyes, because nearly all that casing was stripped away centuries later for building material in Cairo. How did they move stones this size without cranes? Archaeological discoveries over the last 2 decades have given us real physical answers, rather than speculation. In 2018, a research team led by physicist Aaron Rees and engineers studying the Dashur pyramids identified wooden sledges paired with a wet sand technique, where workers poured water onto the sand in front of a sledge, cutting friction dramatically and allowing far fewer workers to drag enormous loads across the desert. An ancient tomb painting from Deir el-Bersha showing a giant statue being hauled on a sledge with a man pouring water just ahead of the runners had puzzled Egyptologists for a century until physicists at the University of Amsterdam tested the exact mechanism in a lab in 2014, proving that wet sand can reduce friction by up to half. Show that tomb painting on screen, then cut to the lab recreation, sand and sledge, water poured, the block gliding forward with visibly less resistance. Then there's the ramp question, one of the oldest debates in Egyptology. For decades, textbooks favored a single long, straight ramp theory, but the sheer volume of material such a ramp would require made many researchers skeptical. In 2018, French architect and Egyptologist Jean-Pierre Houdin, working alongside engineers, proposed an internal spiral ramp theory, supported by muon scanning technology from the Scan Pyramids project, an international collaboration using cosmic ray imaging to peer inside the pyramid without disturbing a single stone. That scan, published in the journal Nature in 2017, revealed a previously unknown void above the Grand Gallery, a discovery that reignited global interest in how the interior of the pyramid was actually constructed and used during building. Show the scan data itself, glowing outlines of hidden chambers rendered in false color, a visual that looks almost like an X-ray of a 4,000-year-old secret. And what about the workers themselves? For generations, popular imagination pictured slaves under the lash, an image cemented by Hollywood more than by evidence. But excavations led by Egyptologist Mark Lehner and Zahi Hawass at a nearby settlement now called the Lost City of the Pyramid Builders uncovered bakeries, breweries, and worker housing capable of feeding thousands of people a day, along with evidence of medical care for injured laborers, including healed fractures that had clearly been set and treated. Show the excavation site, rows of ancient bread molds still sitting in ash, a reconstructed CGI workers' village. These were not enslaved people worked to death in secret. They were, by all current evidence, seasonal laborers, some conscripted as a form of tax obligation, and others skilled permanent craftsmen, fed, housed, and cared for as part of a national construction project of almost unimaginable scale. Now travel across the ocean and up into the clouds to Machu Picchu, where the Inca faced an entirely different engineering problem: how to build a permanent city on an active fault line, on a ridge between two mountain peaks, in a place that gets battered by seasonal rain capable of triggering landslides. Their solution was not to resist the mountain, but to work with it. Inca masons used a technique called ashlar masonry, cutting stones so that each block interlocked with its neighbors in complex, almost puzzle piece patterns, with no mortar at all. Show a close-up drone shot gliding along one of these walls, the seams between stones nearly invisible, sunlight raking across the surface to reveal just how tight the joints really are. This irregular, interlocking design was not decorative. It was, according to structural engineers who have studied the site, a form of ancient earthquake proofing. When seismic waves hit a mortar-bound wall, the rigid structure cracks and crumbles. When they hit Inca stonework, the individual blocks can shift slightly against one another and then settle back into place, dissipating energy the same way flexible modern skyscrapers are designed to sway rather than snap. A study conducted by researchers modeling Inca wall behavior under simulated seismic stress, published through engineering research on Andean architecture, showed that these interlocking joints allow movement of several centimeters before the wall returns to its original position, a level of resilience that some modern rigid concrete structures cannot match. Show a diagram animation here, a simplified wall cross-section vibrating under simulated seismic waves, stones flexing and resettling, while a smooth mortar wall beside it cracks apart. Machu Picchu's builders also solved a drainage problem that would defeat many modern engineers working in similar terrain. The site receives enormous seasonal rainfall, and left unmanaged, that water would saturate the mountainside and trigger the very landslides the Inca needed to avoid. Beneath the visible terraces and plazas, archaeologists have mapped an extensive drainage system, layers of gravel, sand, and larger stones arranged to funnel water away from buildings and out through carefully placed channels, some of which still function exactly as designed more than 5 centuries later. Show a cutaway CGI illustration of a terrace, exposing the hidden layers beneath the visible grass and stone, water flowing invisibly downward exactly where the builders intended. And how did they cut that granite without iron tools? Evidence from quarry sites nearby shows Inca workers used harder stone hammers, called hammerstones, to slowly pound softer granite into shape, combined with a technique of heating stone with fire and then rapidly cooling it with water, causing controlled fracturing along natural stress lines. A slow, patient process, but one requiring no metal at all. Now to Baalbek, and to a mystery that even modern engineers with hydraulic cranes find genuinely humbling. In the Roman-era temple complex, 3 stones known collectively as the Trilithon sit in the foundation wall, each measuring roughly 19 meters long and estimated to weigh close to 800 tons apiece. Nearby, in a quarry less than a kilometer away, lies an even larger unfinished block, nicknamed the Stone of the Pregnant Woman, or more recently, the Stone of the South, weighing an estimated 1,000 tons, still attached to the bedrock it was being cut from when work stopped for reasons nobody has ever explained. Show a wide drone shot of that quarry stone lying in the dirt, dwarfing the workers and tourists who walk past it, a scale almost impossible to communicate without seeing a human being standing next to it for comparison. How do you move 1,000 tons of solid limestone without modern lifting equipment? German archaeologists working with the German Archaeological Institute have spent years studying the quarry and surrounding terrain, and their leading theory, published through ongoing excavation reports in the 2010s, involves a system of wooden rollers, ramps, and enormous teams of oxen or human laborers pulling in coordinated unison, guided by a slight downward slope engineered into the transport path itself to use gravity as an assistant rather than an obstacle. Show an engineering diagram animation, ropes fanning out from the stone to dozens of pulling points, a shallow ramp descending gently toward the temple site, arrows indicating the combined pulling force required. Some estimates suggest moving the smaller trilithon stones would have required several thousand people pulling in perfect coordination, an operation that speaks less to secret lost technology and more to extraordinary organizational discipline, precise timing, and deep practical knowledge of leverage, friction, and rope tension passed down through generations of quarry workers. It's worth pausing here to separate fact from fantasy, because few ancient sites have attracted as much speculation as these three. The idea that the pyramids were built by aliens, or using anti-gravity technology, or by a lost advanced civilization predating Egypt, has circulated in popular media for decades, but it collapses under the weight of the evidence archaeologists have actually found. Worker villages, ramps, tool marks matching known Bronze Age copper chisels, quarry inscriptions naming actual work crews with names like Friends of Khufu, and construction techniques that leave visible signatures in the stone itself. Show a close-up of copper chisel marks still visible on unfinished blocks at Aswan. Baalbek has drawn similar speculation, sometimes framed as evidence of a vanished pre-Roman super-civilization, yet the archaeological layering at the site clearly shows Roman-era stonework techniques and tool marks consistent with the 1st century BCE, built atop earlier Phoenician religious foundations, not some unexplainable prior epoch. Machu Picchu, too, has been credited to everything from ancient astronauts to Atlantean refugees, when the actual evidence, tool marks, unfinished blocks left mid-carving in nearby quarries, and clear continuity with other confirmed Inca sites across the region, tells a more grounded, but no less astonishing story. This was the work of human beings, solving human problems with extraordinary skill. None of this diminishes the mystery. If anything, understanding the real methods makes the achievement more impressive, not less, because it means ordinary people, without modern machinery, organized labor, physics knowledge, and sheer willpower into something that still humbles trained engineers today. Modern science continues to add new layers to these stories every few years. The Scan Pyramids project's muon tomography, essentially using naturally occurring cosmic ray particles to see through solid stone the way an X-ray sees through skin, represents one of the most exciting developments in Egyptology in a generation, because it allows researchers to study the pyramid's interior without drilling a single hole. Meanwhile, geologists studying Roman concrete used extensively in structures built around the same era as Baalbek's temple complex, discovered in a 2017 study published in American Mineralogist, led by researcher Marie Jackson, that seawater reacting with volcanic ash in Roman concrete over centuries actually grows new mineral structures within the material, making it stronger over time rather than weaker, the opposite of how modern concrete behaves. Show a microscope image of that mineral growth, strange crystalline structures forming inside 2,000-year-old concrete samples. The single discovery has already influenced modern efforts to design longer-lasting, more sustainable concrete, proving that ancient engineering solutions are not museum curiosities, but active sources of inspiration for the materials science of tomorrow. And the legacy of these sites runs deeper than most viewers realize. The precision surveying techniques used at Giza, involving careful astronomical alignment, with the pyramid's sides oriented to true north within a fraction of a degree, likely using observations of circumpolar stars, laid groundwork for surveying principles still taught in civil engineering programs today. Show an animated night sky sequence, stars wheeling around a fixed point as ancient astronomers track their positions against a plumb line. Inca seismic-resistant stonework has directly influenced modern earthquake engineering research in Peru and Chile, where architects have studied interlocking joint systems for use in contemporary buildings designed to survive major seismic events. And Roman engineering principles visible at sites connected to Baalbek, including arch construction and load distribution, form the direct ancestor of engineering techniques used in bridges, aqueducts, and domes for the next 2,000 years, echoes of which appear in structures built well into the modern era. Standing at any of these sites today, Whether at the base of the Great Pyramid with your neck craned back to take in a structure that has outlasted every empire built since, or high in the Andes watching mist roll across granite walls that have shrugged off centuries of earthquakes, or beside a 1,000-ton stone still sitting exactly where its builders left it, unfinished and unexplained, you are standing in the presence of a fundamentally human achievement. Not magic, not aliens, not a lost super-civilization erased from history, just people, using fire, water, rope, patience, mathematics, and an almost unreasonable stubbornness, refusing to accept that something was impossible simply because no one had done it before. So here's the question worth sitting with as this story closes. Every generation looks at the achievements of the one before it and assumes those people must have had help, must have had secrets we've since lost, must have known something we don't. But what if the real secret was never a lost technology at all? What if it was simply organization, patience, and the willingness to spend decades, even entire lifetimes, working towards something no single person would ever see finished? If that's true, then the real question isn't how they built the impossible. It's what we, with all our modern tools and machines and knowledge, are still failing to attempt because we've convinced ourselves it can't be done. What would you build if you knew you had the next 20 years, and total belief that it was possible? Let us know what you think down in the comments below.